So then we get into Gibbs free energy. Gibbs free energy, and again we could go higher than this too. This gets much more complicated in thermodynamics and as you get into physics, etc. We're just going to use it to determine whether a reaction is spontaneous or not. Now I want you to, most of you, if you think of spontaneous, like spontaneous combustion, something just happens like instantly. Spontaneous does not need to be instant. Spontaneous means it doesn't really require any outside interference. We don't really need to have a change in temperature or anything to take place. This reaction is going. For example, if you set iron outside, it may take 3-4 weeks, but that iron will eventually rust. That is a spontaneous reaction. Okay, nuclear decay. Nuclear atoms, it may take 1 billion years, but usually they'll end up decaying. So those are spontaneous, means it's going to take place with really any outside interference. Mainly we think of changing the temperature on that. So this is important. When delta G is called Gibbs free energy. Gibbs free energy measures whether or not a reaction is going to take place without any outside interference. We call it spontaneity, whether it's spontaneous or not. If delta G is negative, the reaction is spontaneous. I was watching a gentleman the other day, and he was saying this is how he helps his students. He says when you go to make a G, he says you put that little line there. That's the negative. That might help you remember. I thought that was kind of cool. So the little negative there on the G, that means it is spontaneous. The spontaneous. Never seen that before. So delta G was negative. It's going to be a spontaneous reaction. The forward reaction is spontaneous. If it's positive, that means the reaction is going to need you to put some energy in or do something. Something's going to have to happen because it's just not going to happen by itself. For example, if you have a rubber band, okay, if it's stretched out and you let go of it, it's just going to go back together. That's spontaneous. But if you have an unstretched rubber band just sitting there, it's not going to just stretch out. You're going to have to put some energy in to do that, to make it stretch. So that's kind of a good example. So delta G positive, it's not spontaneous, not spontaneous. And then when delta G is at 0, the reaction is said to be at equilibrium. That means that forward and backwards reaction is going back and forth pretty much at equal rates with one another. So here's some examples of spontaneous. I like the little guide. This is from the textbook. So if you've ever skied, if you could just kind of barely shove yourself, you still have to get over activation energy. Everything's going to have activation energy. But a little push will send you down the hill and you just kind of keep going. But you're just not going to spontaneously get yourself back up the hill unless you put some energy in it. Okay. And so again, spontaneous doesn't mean it happens in an instant. If you're at the top of the hill, you're not just going to instantly be at the bottom. It may take some time, especially if you're a really slow skier. So again, spontaneity is not necessarily instantaneous. Water running downhill, lump of sugar dissolving, water freezing below 0 and ice melting above 0, heat flowing from a hotter object to colder object. So these are all examples of things that are spontaneous, that are favorable conditions that just tend to happen. That's another thing you can think of it as a favorable condition. Also like this from your book as well. So if we had a bunch of gas molecules in a sealed off container and the valve's shut here, if I open this valve, we have diffusion. These gas molecules are just going to evenly spread out. This just happens. Diffusion absolutely just happens. But if you had this situation, they're not all of a sudden just going to go ramming themselves back up in here unless you had a vacuum or something to suck them back up into there. So this would be a spontaneous. This would be spontaneous, and this would be an example of non-spontaneous. Again, spontaneous doesn't mean instantaneous. It just means it's going to happen without much outside interference. And to calculate that, there's two ways. Does that one look familiar? If you are given G, which is another column, it works just like the H and the S. You're going to take the products minus the reactants. So that's fun. We're not going to work one of those. But then you have this other one, and this one is more common, so this is more likely what you're going to be doing more often, is delta G equals the change in the enthalpy minus, and this needs to be in a parentheses together because sometimes students make a mistake and they don't put them together. This T stands for temperature, and this temperature is going to need to be in Kelvin. So this needs to be in Kelvin. Remember, to get to Kelvin, you just add 273 to your Celsius times your delta S. We do have a problem though, and our problem is that this guy was measured in kilojoules, and this guy was joules per mole Kelvin. They're both joules per mole, but let me get the moles out of there because moles are there. But so joules per Kelvin. Well, that temperature, Kelvin's going to take care of the K. The problem is this one's a J and that one's a KJ. So in order to subtract those, you're going to need to change this. So what that means is, before you do this problem, you need to divide by 1,000 to get your joules into kilojoules, because you're going from a smaller unit to a larger unit. So before you use this, so you'll calculate the S, some of the products minus some of the reactants, and before you use this equation, you'll divide by 1,000 before you subtract them. Alright, so let's do one of those. It says calculate the Gibbs free energy for the reaction of nitrogen, hydrogen. Oh, this sounds familiar, doesn't it? So we had this equation a while ago. So we've got nitrogen plus 3 hydrogens making 2 ammonias, and these were all gases. And we actually found the delta S in that previous problem to be a negative 202, and this would be joules per Kelvin, joules per mole Kelvin. Technically the moles have canceled out, joules per Kelvin there. And I should have told you all ago that Gibbs is measured in kilojoules. So delta H, kilojoules, we've got Gibbs in kilojoules, but entropy is such a smaller value, they just measure that in joules. I am sorry they don't just all do the same thing, it's just the way it rolls. Okay, entropy is such a small amount of energy, it's measured in the joule unit instead of the kilojoule unit. Alright, so if I calculate delta H, again, some of the products minus some of the reactants, I would have 2 times, and I would go up to the ammonia. So I put on here, notice this is that same chart from delta H. So there's ammonia, negative 46.2. So let me go here, negative 46.2. That is kilojoules per mole. I'll go ahead and write it. But y'all know that is moles there, and the moles are going to cancel out. And then we would minus the sum of their reactants. But what do we know? This is delta H, not S, but H. Well, that's a pure element, and that's a pure element. So this side is actually 0 there for delta H, enthalpy, not entropy. So delta H here is a negative 92.4. I'm just going to put kilojoules, because technically the moles have canceled with this guy, which is mole. There. Okay, so I have H, I have S, I have a temperature. So delta G is the change in H minus the T times the change in S. But S needs to be changed. So if you want to write yourself a note, you could do this. Like that, because we know we need to do that. Okay? So delta G, so this guy is a negative 92.4 kilojoules minus, that needs to be in Kelvin, so 25 plus 273 is 298 Kelvin, and this was negative, but it's going to be 0.202 to change it to kilojoules. Can you see the kelvins are going to cancel here? And technically the moles have canceled a while ago. So I would tell you to not run it all together, but completely up to you. And this, if I multiply that together, you're going to get a negative 60.196, and you're going to get kilojoules. Can you see those two negatives there going to make a positive? But this is not a big enough number here to overcome this number, so therefore it's going to stay negative. That's kind of important because I want you to see that both of these are negative here. But my temperature wasn't great enough to make this number big enough to overcome this. So at this lower temperature here, we're still going to get a negative value of negative 32.2 is what I got. I think it's 0.15, but for sig digs, well, 2.2 kilojoules. So is this spontaneous or non-spontaneous? Spontaneous or non-spontaneous? This is spontaneous. It's a spontaneous reaction. So the making of that ammonia does happen. Yeah, it's not a real fast process, but it does happen. But I just want to show you here. If I had got this temperature, let's say 1,000 degrees or something of that nature, I mean, we got it like really hot. We got it really hot. Can you see that this would become a really big number, and all of a sudden this would be two positives and this number would be bigger than that, and now all of a sudden this would be non-spontaneous? So making of ammonia, if we get the reaction too hot at a very high temperature, it all of a sudden will not be favored anymore and it won't happen. So this relates back to something we learned before. This is an exothermic reaction. I know it's exothermic. Look, delta H is negative. So my kilojoules would be over here. And in a Le Chatelier's principle, if you add too much energy, it's going to cause that reaction to shift this direction. So if we get it hot enough, remember this gets back to equilibrium, if I get it hot enough, I'm going to actually start making the other direction. That would be the favorable condition there. So all this stuff just kind of rolls together. It's crazy, I know.